Hi, I'm Joy from University of Bonn. The title of my talk is Refined Large Deviation Principle for Branching Brownian motion conditioned to have a low maximum. This is a joint work with Professor Lisa Hatton from University of Mainz, and we also thank Professor Anton Bovie from University of Bonn for his support. The structure will be like this. First, I will introduce to you what is a branching Brownian motion. Secondly, I will talk about previous results on branching Brownian motion conditioned to have a low maximum. Lastly, I will talk about how our results refined previous results. So, what is a branching Brownian motion? It can be constructed like this. Starting from one particle at time 0 at the origin, it does standard Brownian motion. After some exponentially distributed time, it splits into two particles, each following independent Brownian motions. And this process is repeated indefinitely. There are some known facts about branching Brownian motion. The first thing is that the number of particles grow exponentially with time. The other thing is that the order of the height where the maximum particle can achieve is of order square root 2t at time t. We are interested in constraining the maximum level of branching Brownian motion, which is described as this probability here, where the maximum particle needs to stay below the level square root 2 alpha t, where alpha is less than 1. This was studied before in 2016 by Deviation, where they gave large deviation estimates for this probability. The idea behind their proof is quite interesting. Recall that each particle in a branching Brownian motion after its birth follows independent Brownian motion, and that's why we can use recursive thinking. Suppose the initial particle doesn't branch until some time tau at location y. Because it doesn't branch until time tau, it pays a price e to minus tau because the branching time follows exponential distribution. And it pays this Gaussian density because it follows Brownian motion. At this point, it splits into two particles, and each of them forms independent Brownian motions from their birthplace. The remaining time for them to travel is t minus tau, and the maximum level they can reach is square root 2 alpha t minus y. And that's why we have this probability squared. We integrate over all possible first branching location y and first branching time tau to get this first summand. There is still another part of this which contains the case that the initial particle doesn't branch at all, and this completes the equation. By computing these integrals, we can obtain large deviation estimates for this probability. In the process, there are certain neighborhoods of y and tau that will dominate the whole estimation, and those y and tau are what we call the optimal choices. We denote them as tau 0 and y 0. In other words, it means that if you give me an alpha, then I can give you a tau 0 and y 0, which forms this green dot on the time location plane. And if your BBM chooses to do its first branching there, then it's more likely to stay below the square root 2 alpha t level. This recursion idea has some interesting intuition behind it. For a branching Brownian motion to have a low maximum, there are some good behaviors that it should follow. The first is that the initial particle should branch at a late time tau, because if it branches early, then we will expect a lot of children at the end, which is hard to control. The other good thing is that the initial particle should branch at a low location y, which gives its children a good starting point. Thirdly, the two children as independent branching Brownian motions should also have low maxima themselves. There is an interesting analogy to it. Suppose we have a family which starts from one parent, and this family wants to avoid bankruptcy. What should they do? Well, the first thing is that the parents shouldn't give birth to children at a young age, so that she wouldn't expect many children, grandchildren, and great-grandchildren who are hard to control. The other thing is that the parent herself should have a healthy financial situation so that her children have a good starting point. The last thing is, of course, her children have to stay financially healthy so that the family wouldn't go bankruptcy. Okay, enough analogy here, and we're back to math. Recall that we have these three factors. Each of them contributes to a low maximum BBM, but all of them has a price associated with them. Therefore, we are interested in the interplay between these three factors, and that is why we are trying to refine the previous result in adding this new event there, which refines the first branching time and first branching location of the initial particle. In our paper, we present the large deviation estimates for these four probabilities. They look complicated, but essentially what they say is that given any alpha and on this plane, we cannot choose this green dot. And we are curious about the probability of choosing any other dots on this plane. The first probability refines the first branching time to be within 0 and gamma t, where gamma can be any number from 0 to 1. On the picture, it looks like this. Suppose the first branching can only happen in the gray area, and for gamma in 0, 1, it spreads into the whole area between 0 and t. Suppose we choose a gamma like that, then our results tells you a best time location combination that a BBM should choose to have a low maximum. However, this doesn't cover everything about the first branching time, because if our gray area covers the optimal location in the unconstrained case, then the BBM should do what the red trajectory does, which is to branch at tau 0 and y 0. Therefore, we have the second probability there, which controls the branching time to be after tau 0. On picture, it looks like this. Next, we want to control the first branching location given the first branching time. So, in this probability, we fix the first branching time to be within an epsilon neighborhood. On picture, it looks like this. You can choose anywhere from 0 to t again, and let's suppose it chooses there. Then our probability restricts the first branching location to be below this yellow line. Essentially, you can choose everywhere depending on your beta, and let's say it chooses there. Our result will tell you the best first branching location to choose and also the large deviation estimates for this probability. Likewise, we also have a probability which restricts the first branching location to be above the optimal y. Again, your first branching time can be fixed at anywhere, and let's suppose it's there. We restrict the first branching location to be above this yellow line. And depending on your beta, you can choose anywhere above, let's say there. And our result will tell you an optimal choice of location and large deviation estimates for such a BBM. Our method is fairly simple. We use recursion again. And because of this previous result, there is only one mild modification that we should do in the computation. Okay, that ends my talk. As a summary, we present previous results on BBM conditioned to have a low maximum and their main idea behind the proof, which is recursion. We then present our results where we refine the previous results in adding this new constraint on the first branching time and location. The previous result choose that green dot, and our result essentially tells you what is the probability if you choose any other dot on this time location plane. The idea, again, is recursion. Thank you very much for listening.